Good morning, everybody, to our second day of the MTS2025. My name is Dagmar Triesnack. I'm the host of the room AB. And before we get started, I have to make some announcements. So today it's the final day also for the Solutions Hub and the programming there. There's a lot to see in the Solutions Hub, including live demos for the 3 topics: acquisition and live capture, post-production, and delivery over ATSC 3.0. There will be, of course, the technical sessions in the 2 rooms, and we have several breaks where we serve coffee, and we will have a lunch in the Solutions Hub later. And tomorrow, on Thursday, we have a DJ battle between the SMT president Rich Welch and Juan Reyes on Thursday. There will be signs around in the convention center with QR codes where you can vote who will win. And talking about QR codes, we have the QR codes here for the questions in the room for the sessions. And I guess that's what I need to say. And I would like to hand over to Willem for the first session for DMF.
Thank you so much. I saw your name was spelled wrong this time. Yesterday it was spelled correctly. So good morning, everyone. My name is Willem van Most, work for the EBU, and I'm honored to be your chair of this session today. So who was in the room yesterday and saw Félix Poulain and Thomas Edwards presenting? Oh, that's quite a huge deal. So that's why you're probably here today, because actually we're going to continue a little bit. So we had a good overview on what the DMF was. Then we had a deep dive into MXL, but I can guarantee you, if you're still hungry for a little bit more deep dive, we have colleagues from Riedel, and those colleagues will go even deeper today. So I'm proud to present Sithideth today. Sithideth, and now I need to read a little bit, is the director of the incubator group at Riedel. And, well, we've seen and know him for years. He's a pillar in the industry and working on DMF and MXL as well. And he brought along his colleague Jonas, and together they did a deep dive into lip fabric. I'll leave the unraveling of the magic of lip fabric to them. So Jonas and Sithideth, the floor is yours.
So good morning. I will try to be as entertaining as possible this morning. At least if I'm not entertaining, then I'll be informative. So we'll talk about the device memory sharing, the study we made, especially regarding high performance internode and GPU memory sharing in the context of the media exchange layer. So you know that the MXL group, we work on this for quite some time, maybe a year now, and we were focusing on exchanging memory within a single compute host. And now we're looking at, expanding this to do, sharing memory or moving memory around between GPU and host CPU and across the network also. So that is going to be the gist of our presentation today. So the agenda is going to be quite simple. Why would we need efficient data movement between these compute hosts, compute nodes? How we conducted our study, because these movement of memory are kind of, complex, and they can be, hard to understand, and how we would have framework to help us alleviate some of this complexity. And of course, what is really interesting is the results, right? In terms of latency, compute costs, how it is easy to use, right? That's going to be our impression of this. So why would we need efficient data movement, right? So in the DMF MXL, there's an SDK that we build. It is open source, and it also helps broadcaster vendors focus on their software, what media function they want to do. How can this be different, right? How can we move data around and say, well, I have a scaler somewhere, and then it needs to interact with a multi-viewer across the network that lives on a GPU. That opens up all these possibilities, right? So that's why we need efficient media sharing. Also, all these pipelines, all these clusters, right? They need to be at the basis interoperable. So you, as a user, as a vendor, you have to care as little as possible about, is it going to work with vendor A, B, C, and D, right? So that is the essence of the open source SDK that we provide. So the DMF MXL, they build, I think, Felix is here, William is here. They built this, super cool layered approach where the media function sits on top, then the exchange layer, be it what it is, helps these media function interact together, and that those media function and this exchange layer sits on top of a container platform, right? So you could, spin them up and down as you want, and then they would, interact properly. So you don't really have to care about these things, but where 2110 or something like transport, you really would have to care about, well, what I'm connecting, where is it? Is it going to be decoded because it is a spec, being an SDK? Hopefully you don't have to care too much about this. And then, so also we want to have the possibility of choosing the best hardware, right? Because not all compute are equal. So maybe you have a CPU from vendor A, a CPU from vendor B. Maybe it does something better for specific compute, some processing, or you have a scaler that is really optimized for GPU, right? You want to be able to leverage that. So, but you need also interaction with other, media function. So those memory movement have to be, efficient. Also, it has to work in a cluster, and we will look at how a, framework such as UCX from NVIDIA and the Fabric can help us, abstract some of these complexity for us. So how we conducted the study? First and foremost, I just want to give you a quick timeline. So somewhere around March this year, we, as vendors within the DMF Tiger team, we achieved first, we built code together and have memory sharing within a single node. So that was a great milestone, and we made that work public somewhere in May this year during the EBU MTS. In the meantime, we thought about, hey, how can we share, memory across the network? So that's where we thought about a, MXL Fabric API. While we were doing that, we said, well, the principle are kind of the same if we want to move memory around, let's say, between two GPUs or GPUs across the network. No, the principle are the same. I'm not saying it is completely, the same, but the building blocks are the same. So that's why we thought about this, and that's what we want to explore and share with you guys, how we conducted a study between, moving memory around GPUs across the network. So we can have the understanding what is a compute node in a cluster. And I wanted to have this picture. I think it was really important. So a compute node would consist of one or multiple GPUs, one or multiple host CPU, and it would of course have a network interface card. And then these clusters of compute node would be tied together through a Rocky enabled Fabric network and sharing media through RDMA. So what are the type of memory movement or memory sharing, right? The common ones are if you're inside a host, you have multiple process, multiple media function that would share, a single portion of the memory. So you don't have to move memory. It's just two pointers pointing at the same place. And then you would have the host-to-host memory sharing, right? You would have, memory from a process that lives in a compute node on the host memory, and then you would do RDMA without having to, go copy to the network card directly to the network, on the network, and then receive that on a separate compute host CPU memory that we would call, interhost memory transfer through RDMA. And then the less common ones would be, if you would have a GPU and a host CPU, how would we move memory around between these two entities? So that's what we call host to device and device to host, where the only thing that you would use is PCI bandwidth, right? And then you could have also GPU to GPU within the same compute node. So that's what we call device to device. So pretty simple. And then the more complex one is, let's say you would want to move memory between one GPU in a compute node, and then across the host memory on the CPU, go through the network, receive that on the host CPU, and then to the endpoint GPU, which do the final computation, right? That would be the device to host to host to device. And then you can bypass the host CPU. So you would say, no, on a compute node, GPU process directly on the network, receive that on a separate compute host GPU. So that's the different type of movement. And then I think the interesting part is the results and experiments. So I will hand off to Jonas.
Hello, check. Hello. I'm not online yet. Now I'm online. So what did we do? That's our stack that we use for testing. We have two compute nodes. They are running Proxmox Virtual Environment 8.2. That's basically maybe VMware is more commonly known. It's a hypervisor. It's based on Debian. And then we have two virtual machines running on each of these nodes, running Ubuntu 24.04 with the Linux kernel 6.8. And then we pin those virtual CPU cores of our virtual machines to the NUMA nodes where our hardware is attached to. So there's no inter-NUMA effects going on. We also configure our NIC and our GPU in pass-through. So they are mapped directly into the virtual machines. There's no memory translation going on between the virtual machine and the host. And so they present to the virtual machine exactly like they would to a bare metal host. And then we have those two VMs through the NICs connected with 100 gigabit Ethernet to a switch that supports everything that we need to do proper ROC EV2. That is what we did our experiments on, and that's also the system that you will see the results from here, but we've run the same tests also on different environments, bare metal, on Kubernetes. That also works. There's no real limitation there. It's just that we like to use VMs for like archiving our dev environments and rolling back stuff when we install something that we can't get rid of anymore. Yeah. So that's our test harness that we've built to accelerate a little bit our testing process. It's a C++ application that we've, by the way, published. There will be a link later on the slide where you can look at all that. It's really simple to use, hopefully. It uses, so if you can build MXL on your system, you will also be able to use that because it's using the same build system, same base sources and everything. And it consists of a runner and a reflector. And the runner has an initiator that initiates a transfer to the memory of the reflector. And then immediately after that, the reflector will initiate a transfer back into the memory of the runner. And between that is where we measure the latency. If you see those frames there, that is actually in case where we use host memory, that is actually MXL ring buffers. So if you remember the talk from Thomas yesterday, remember those ring buffer structures, that is what these frames are here. The tests are basically fully automated. If you want to run this at home, you just give it a list of things that you want to run, and the runner will configure the reflector over HTTP, and then you can run your test. And we use Perf internally to collect CPU usage, and latency is measured by sampling the system clock. libfabric, there's a little bit of a caveat here. We not only use libfabric, but what we use is actually our pull request that we've opened a while ago on the MXL project, and that will hopefully become the MXL inter-host memory sharing implementation. So whenever I say libfabric, that is actually what maybe will land in MXL soon. Key metrics that we're interested in, obviously latency, always very important in broadcast, but also CPU usage. Ideally, you want your CPU not doing boring transfer stuff, but more interesting processing, and also the PCI bandwidth. We've chosen this round-trip latency measurement, but there was a little bit of a question before if that maybe influences the results. But what we did here is we did a comparison between measuring the latency as half of the round-trip time versus doing only a one-way transfer, and measuring the latency by tightly synchronizing the clocks on the two machines and then doing the actual one-way latency. And you can see it is basically the same. So there's no influencing the one-way latency by doing a ping pong. So the first set of results, the data path comparison. So what we're interested here is the difference between doing a transfer device to device over the network. So for example, from a GPU to a GPU on another host, versus going a more traditional route, first transferring to the host memory on one device, then going over the network to the host memory on the other device, and then going to the device memory. And there's probably nobody here really surprised that it is faster to go from device to device directly. It is also a little bit more complex to set up because you have to have the correct drivers and everything has to work together. But when I say it's a little bit more complex, it's really just a little bit more complex because we had no real trouble setting that up. There's a table here that shows in the last two columns also the CPU usage and the PCI bandwidth that is used to do these transfers. You can see the PCI bandwidth for the red ones, which are the ones that do the extra copy to host memory, is double, because you have to go to the host and then back to the NIC, right? You have 2 times the PCI. And the CPU usage is actually 20 times higher. And this additional CPU usage does not come from the network transfer portion, because if you do CPU memory to CPU memory network transfers, the CPU usage is also really, really low. But it comes from the transfer to the device, because that is mediated by the CPU. Okay, our second set of results is the comparison of different frameworks. I can already say CPU usage and PCI bandwidth are basically the same for all of these frameworks, because they do more or less all the same thing. The real difference that we've observed is mostly in latency. Quick overview, libfabric. Libfabric is relatively low level. You, as an implementer of a software that uses libfabric, you have very high degree of control about what you actually want to do. So you have to know the hardware that you're going to use, and you have to set up your transfers in a way that they use the hardware in the best way possible. And it's basically just an abstraction that is verbs-like. So verbs is the Linux native RDMA API. Basically that, but with support for more hardware that is not supported in verbs, like for example EFA, which is the AWS high bandwidth network adapter. Then we have UCX, and more specifically UCP, so Unified Communications Protocol, which is a little bit of more high level library that can do this network or this device introspection and is able to choose the most efficient transfer path for you. So you don't have to care that much about what hardware you have. UCP will look at all that and then calculate for you what's the best way to do a transfer. And then whenever you see native now, native is just the lowest level API that you could use to do something, right? So if I do a network transfer, I'm talking about RDMA core, which is verbs basically. So it's the Linux native RDMA API. When I say GPU memory transfers or GPU to host transfers, it's just measuring the time it takes to do a CUDA mem copy, which is the native call to transfer data between hosts and GPUs. And CUDA mem copy, obviously, it's hardware specific. So if you would want to implement something generic over that, if you're not using libfabric or UCX, you would have to implement this code for every possible device that you want to support. And also some hardware not supported by RDMA core, like for example EFA, the Amazon thing. If you want to do that, you actually have to use libfabric. I think you can also use UCX, but I think only in the next release, but I'm not sure. Yeah. Garrett is nodding, so. So first comparison, this is the latency, mean latency for doing transfers from GPU to GPU over the network. And you can see that basically all frameworks, including native, produce similar latencies. The frameworks are a little bit higher. UCX here is a little bit higher than libfabric, and that comes from the fact that we have to use or that UCX doesn't expose a specific RDMA functionality that we use to wake up the receiving side of the transfer. Because you remember MXL is asynchronous, and usually when you do an RDMA write, there's no notification on the other side. But in MXL, you want a notification on the other side, so you can do your asynchronous chaining of processes. And this specific thing, it's called RDMA write with immediate data, is not natively supported by UCX. So we have to do two transfers. We basically do a remote write and then just a 64-bit empty transfer basically to wake up the other side. But I've been told by people working on UCX that it's not impossible to implement that, and it's more just a question of priority. This one is the comparison of intra-node transfers, so in one single machine between the host memory and the GPU memory. You see here that libfabric's performance is not that great. Also UCX performance is not that great. libfabric, we've brought that up with the maintainers, and it turns out there's already a fix for that. That will be in the next version of libfabric released in December. And then you get basically the native performance, because then libfabric, all it's doing is also just calling CUDA memcopy under the hood. And UCX also not that great, and I will tell you more about that on the next slide, because it turns out it's also not that great the other way around. If you go from device memory to host memory. And it also turns out, we've also talked with a UCX engineer about that. And it's also that there's no efficient transfer path just implemented in UCX for that specific use case. But it's also not impossible to implement one. On device to device, so going from one GPU to another GPU in the same host, we see that everything performs pretty much similar. Also note the scale here is different than on the other graph, so it's all below 1 millisecond basically, which is nothing. UCX here also suffers from the fact that we are using exactly the same APIs. So even though we are not doing any RDMA here, we still have to do a write of the memory to the GPU and then do another basically just message passing to the other process to wake it up and tell it, okay, now the transfer is completed, because we can do that natively with libfabric. This is UCX performing on another cluster that was not our test system, and just want to show this for completeness, because we've seen that the UCX performance is for device-to-device transfers over the network seems to be fine if you configure everything correctly around it. And we've since found out, after this presentation was submitted, what the problem is. And it's just an environment variable that you have to set to disable a feature that is actually very useful if you have a large network and you want to basically spray your packets around the network to take multiple different transfer paths, which we don't want to do here, but it can be beneficial. But if you disable this feature, or if UCX is able to detect that it doesn't need to use this feature, it can perform equivalent to all the other ones. Okay, some conclusions. We've seen there's all kinds of different data transfers that we can do, that we need to do. We can also do all of them through the MXL Fabrics API, so the thing that we are hopefully going to merge by the end of this year. We've also seen, okay, device to device over the network is much faster than device to host to device over the network. And we've also seen that if you configure everything correctly and your platform is, or your library is supported correctly by the platform you're running on, then these frameworks do not add any significant penalty to your system. And we think like, we've implemented this with LibFabric now, but in general, you could use both of those libraries to do these kinds of transfers. It's really a question of on your platform that you're running on the specific setup, what you have you tested and verified that it works with the setup you're running? Because there's so many factors influencing this. Like, for example, how far your GPU is from your NIC in terms of PCI topology, or if your GPU is directly connected to the same NUMA node as your NIC. And you can really build a lot of very interesting invariants by screwing this up, basically. And that's it. Thank you very much. You can access all this data and much more data actually on this GitHub repository. You can go there and then navigate to notebooks/MTS study. You will see all the data again and more. And I think it's actually rendering in GitHub, so you don't need to clone anything. Yeah, and also the code is there. I totally forgot to write a README for this, but I will, I promise. And yeah, thank you very much. That's it.
Well, thank you so much for a brilliant presentation and some scientific work, which is really needed. Meanwhile, questions are pouring in. So if you scan the QR code, you can put your questions in, or maybe you can raise your hand and just ask it. Let's kick off with one of the questions we see here coming in. In inter-host transfer, what do you see as the biggest bottleneck for future multi-host media processing architectures?
Bandwidth? But it's a soft impediment, I would say. As the speed and bandwidth increase over the time, I don't see that as a real strong,
If you mean bottleneck in terms of the ability to transfer more and more data, it's bandwidth, yes. If you see bottleneck as the maybe rate of adoption or this gaining traction, it's maybe platform support, so a way for people to run their applications on that just works, right? And also I think there's a little bit of an unknown in how will this behave when you have not only one single test running, right? Because we are only running always one transfer at a time over this network. And that's also why our latencies are basically very close to the theoretical minimum that you can do over 100 gigabit. As soon as you have other stuff running, there will be other effects, right? You're going to need to use flow control to mediate some of that. And I think that's also a possible next topic for us. Yeah.
Okay, I see a hand raised here, so we have a live question, and I'll bring you the mic.
Hi guys, brilliant presentation. That was my question about bottlenecking. And I think one of the things I'm interested in, which I think you just started to hint at then, is when we get multi-flow, because if you look at the number of milliseconds there, you look at the frame period, it's actually representing a fairly significant proportion of frame period, even though it's, a relatively small, tiny bit of 100 gig interface. So, is it the external connectivity bandwidth? Are you suspicious of any internal PCIe bandwidth challenges? And in terms of CPU loading and management of those transfers as well. So do you see any kind of red flags as we move forward with this of infrastructure challenges that actually are going to create real world limitations, or do you think we need to do more testing before we actually can determine that?
I don't know if we need to do more testing, because this is not new technology, right? And the whole billions of dollar AI and machine learning space is using this every day. Not with the real-time and latency requirements that we have, but also, right, one thing with MXL is the move from synchronous hard real-time to asynchronous processing with a synchronization at the end. But what is a real thing is that people will have to care about how they are laying out their hardware. So you really if you know that you want to do a lot of GPU to GPU transfers over the network, it is very beneficial to put your GPU and your NIC on the same PCI bridge if you have a PCI bridge in your thing. And that means that the platform, right, your provider that you're running your media functions in is becoming a very important component of a very efficient media sharing distribution system.
All right, thank you. There are many more questions, but luckily these guys are still available. So please come after the session to them and ask your question.
Thank you for the NVIDIA guys for helping out.
Oh yeah,
doing this.
Thanks.
We totally forgot that. So thank you.
Well, it's always important. It's always teamwork. A big thank you, applause for the Riedel guys and the NVIDIA guys in the back.